Welcome to The Explainer. Today, we are pulling back the curtain on something you probably use every day without even realizing it. We're talking about the fundamental but kind of hidden engine of modern science and technology, the math that powers pretty much everything, from your weather app all the way to the search for new medicines. And this quote from the one and only Alan Turing really sets the stage perfectly. It's all about solving these huge, immense challenges that are lying just ahead of us, the kind of problems that demand just an incredible amount of computational power. So, what are these problems exactly? Well, we're talking about simulations and models that are so unbelievably complex, they are constantly pushing the absolute limits of what we thought was possible. I mean, just look at this list. The sheer breadth of it is staggering. Designing safer cars, forecasting the weather, modeling the human heart to prevent strokes, even trying to understand the universe itself. Every single one of these relies on a field we call high-performance computing, or HPC. Basically, we're talking about supercomputers. And if you could peer deep inside the code that's running on these massive machines, you'd find a common mathematical problem that eats up a huge amount of time and resources. And that challenge is solving enormous systems of linear equations. You can kind of think of it like the universe's biggest, most high-dimensional game of Sudoku. So how did we deal with this for so long? Well, for decades, mathematicians have had this really, really clever way of tackling it. It's an approach that basically became the workhorse for all of scientific computing. And this idea didn't just pop up overnight. Not at all. It actually started with the Russian mathematician Alexei Krylov way back in 1931. The idea got developed more in the 50s, but it really took off in the 1970s. Why then? Because that's when computers finally got powerful enough to unleash its true potential. So what is a Krylov method anyway? Well, instead of trying to find the one perfect, exact answer in a single, impossibly difficult step, it does something much smarter. It starts with a guess. Then it makes a slightly better guess, and then an even smarter one after that, getting closer and closer to the real solution with every single step or iteration. It's just this elegant, super efficient approach to a monstrously complex problem. And here's how it breaks down. It's a beautiful little loop. You start with a guess, you figure out how wrong you are, that's the error, then you use that error to find a better direction to search for the answer, and you just repeat over and over until your answer is close enough. Simple, right? But also incredibly powerful. For a long time, this was the way to do it. But here's where our story takes a really sharp turn. The world of computer hardware changed, and it changed dramatically. And these classic, elegant methods, well, they started to struggle. They basically hit a wall. I mean, just look at this chart. The raw power of supercomputers has just exploded. We're talking a million-fold increase in just over 17 years. So you'd think, great, that means solving our big problems should be a million times easier, right? Well, not exactly. And here's the real kicker. Processor clock speeds actually stopped getting much faster around the early 2000s. Instead, all this new speed comes from doing many things at once, parallelism. But the biggest problem, the real bottleneck, became the time it takes to physically move data from the computer's memory to the processor. It's like having the world's fastest chef who has to wait forever for their ingredients to be delivered. The chef is ready to go, but they're just sitting there, waiting. And wow, this slide right here tells the whole story. On the left, you've got Fugaku, one of the world's fastest supercomputers. On a test that just measures raw calculation speed, it hits over 415 petaflops. Incredible. But look to the right. When it's running a benchmark based on these classic Krylov methods, its performance just plummets to 13 petaflops. That's less than 4% of its potential. The old algorithms were just starving the processor of data. So this massive performance gap made it painfully obvious we couldn't just rely on faster hardware anymore. We needed smarter math. We needed algorithms that were redesigned from the ground up to be aware of how modern computers actually work. And the core idea of the solution is actually pretty simple to grasp, but it's so powerful. If moving data is the expensive part, the slow part, then for every single piece of data you move, you should do as much math on it as you possibly can before going back for more. This is the central idea behind something called block Krylov methods. There's actually a name for this concept, this idea of getting more bang for your data buck. It's called arithmetic intensity. You can think of it as a measure of efficiency. It's just the ratio of calculations to data movement. And on modern hardware, the higher this number is, the better. This table lays it all out, plain and simple.
The old standard method is constantly going back and forth to memory for little bits of data. It's memory-bound. It's limited by that delivery speed. But the new block method, it's smarter. It grabs a big chunk of data all at once and then does a massive amount of computation on it. It becomes compute-bound. It lets that super-fast chef, the processor, finally do what it does best: compute.
Okay, so that's the theory. But did it actually work? Did redesigning the algorithm to be hardware-aware really make a difference in the real world?
Oh, you bet it did. The results really do speak for themselves. Look at these numbers. For a real-world problem, the standard method took over 12 seconds to run. The new hardware-aware block method, less than 2 seconds. That is a gigantic improvement.
I mean, think about that. A 6.2 times speed up. That's not just some small incremental improvement. That is a genuine leap forward. And it was achieved not with brand new hardware, but with smarter mathematics that finally understands the hardware it's running on. And this is why it all matters so much. A 6-fold speed up isn't just an academic achievement. It's not just a cool number on a slide. It means a climate simulation that used to take a whole week might now take just 1 day. It means a drug discovery model can be run overnight instead of over a long weekend. It literally accelerates the pace of science itself.
Which brings us right back to where we started, but with a whole new perspective. We are building these incredible machines that are 1,000,000 times more powerful than they were just a couple of decades ago. And now, by creating algorithms that can actually use that power effectively, the real question becomes, what previously unsolvable problems are finally within our reach?